Welcome to video 4.3 in our first Principles of Astrophotography series. In this video we discuss the signal to noise ratio.
A large signal to noise ratio means a high quality image, which is the reason astrophotographers sometimes spend dozens of hours on a single target.
This video is based on section 4.3 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensibility. 147, noise. The uncertainty in measurements of the average number of photons received per photosite is called the shot noise, which is equal to the square root of the signal.
This is a particular type of noise. You can read Charlie Bracken's book to learn more about read noise. That's the noise that's introduced each time the camera reads out the pixel, the number of electrons in each well. We highly recommend his book, by the way. So it's the square root of the signal. This is using something called Poisson statistics.
Sounds French.
And what it actually means is you flip a coin. It could be heads or tails. The more times you flip that coin, if you flip it 10 times, you might get 6 heads and 4 tails. If you flip it 1,000,000 times, you might get the number of heads and the number of tails that you get for 1,000,000 flips are going to be relatively close to each other. You're going to get close to 500,000 flips, and then the fluctuations depend on the square root of that measurement. So for example, if you have in your hospital, if you're getting on average 100 patients a day, you can expect it to fluctuate between 110 and 90. Your number isn't necessarily going to be between 90 and 110, but about 2/3 of your measurements are going to fall into that range. So you'll occasionally see an 84 or a 115, but 2/3 of your measurements, according to Poisson statistics, are going to fall within that range. This is the uncertainty. This N represents the noise, which is really the uncertainty in the measurement of the number of photons per pixel. I before E except after C.
Oh, nice. You should have been a physics major. English major.
Yeah.
So you're saying noise is uncertainty. It's not a certain number.
Yeah. It's the uncertainty in a number. So
It's not random?
it's based on the fact that these photons aren't coming in. In the example we did in the previous video, I think we got 190 photons.
Yeah. On average.
On average per pixel. But even if you look at a particular pixel, if it's one of those average pixels, it's going to get about 190. The photons, you'll get one now and then one right after, and then there'll be a space, and then there'll be another one. And they're coming in. It's a random stochastic process. And so there's uncertainty in the measurement of that number, the measurement of the 190. And there's uncertainty in that 190 is going to be the square root of 190, which is going to be something like 15 or 13 or whatever it is. Whatever the square root of 190
Sounds
is.
like statistics.
Yeah, it is. But it's important to understand this because in astrophotography, you want a large signal-to-noise ratio. You want a lot of photons compared to the noise, and that's what the signal-to-noise ratio is. So let's go ahead and define it now.
Principle 148, signal-to-noise ratio. The signal-to-noise ratio of an image depends exponentially on the magnitude of the object. Didn't I already read this? Is proportional to the sensor
Very,
pixel
very
size.
similar, yeah. Because what we read before in the last video was the signal per pixel, the average number of photons per pixel.
All right, so let's see if we can tease out the difference here. Depends exponentially on the magnitude of the object, is proportional to the sensor pixel size, and the square root of the elapsed time, here we go, and is inversely proportional to the focal ratio of the telescope. That was there before.
Yeah.
And the square root of the angular area.
So this is a mouthful for sure. But what we had written before was the average number,
Is that little s or big S?
that's little s,
Okay.
of photons per pixel. And that we got to be KT over LW times P squared over F squared in the very last video. Remember, because they were squared, because we wanted it to be proportional to the area of the pixel, right? Times 10 to the minus MV over 2.5. That's what we had before. So now, the signal-to-noise ratio, signal S, divided by the noise N, which is really the uncertainty in that signal, is S, and we argued that according to Poisson's statistics, that uncertainty is equal to the square root of the measurement.
Okay.
So that's in the previous slide. So now if you take S divided by the square root of S, well, square root of S times the square root of S, this right here is
That's
S.
S. Yeah, I figured that out with the 2.
And then you've got the square root of S in the denominator. One of these cancels one of these.
Square root of S.
And so the signal-to-noise ratio is just equal to the square root
Okay.
of the signal.
Cool.
So S divided by N, the signal-to-noise ratio, is equal to the square root of S. And now if you take this S here and take its square root, this is what you get. So you're taking the square root of KT over LW, that's this part right here, taking the square root of P squared, which just gives P. And then taking the square root of F squared in the denominator is F.
Okay, I get it.
And then you're taking the square root of 10 to the minus MV over 2.5. Taking the square root is the same as raising it to the 1/2 power. And if you raise 10 to the minus MV over 2.5, then you end up with a minus MV over 2.5 times 2, and 2.5 times 2 is our old friend, 5.
Okay.
So that's where this 5 comes from. Yeah, sorry, that was a little fast, but we go through it in more detail in our book. But this is a really cool formula, and we were really proud to work it out. This is a constant that should be roughly right within a factor of 2 or so for almost any system. And I really don't care if it's 2.95 or 3 degrees squared or 1.5 degrees squared. I just want to have a rough idea of what everything depends on, and a rough idea of what my signal-to-noise ratio is. What's the actual signal-to-noise ratio? So note here, though, that the signal-to-noise ratio is proportional to the pixel size. So the bigger the pixel size you have on your camera, 3.76 or 2.9 or whatever, or some cameras have like 5 or 6 micron pixels, right?
Yeah.
Those big pixels are going to give you a good signal-to-noise ratio. And then the smaller your focal ratio, the faster the scope, the better the signal-to-noise ratio.
49, area and signal. The greater the angular area of a celestial object, the more its light is spread out over the sensor, and the smaller its signal-to-noise ratio.
So this is a really important thing, and it relates to, back in my visual observing days, they would talk about objects with low surface brightness. The pinwheel galaxy is considered to be low surface brightness. Why? Because it occupies a big area in the sky, and it doesn't have that much brightness per pixel. So where that is captured here, this length times width, so if this is the pinwheel galaxy, and we've got its length L and width W, it's big. It covers a large area of the sky, so those numbers L and W measured in degrees are going to be big. And if those numbers are big, then the signal-to-noise ratio is going to be small. It's going to have low surface brightness.
Right.
And that's why that galaxy is difficult to see visually through a telescope. You're just not collecting that many photons. That's what this is trying to say. The angular area is L times W. L is the length measured in degrees. W is the width or the height, whatever, measured in degrees. And the bigger those are, the smaller the signal-to-noise ratio is going to be. Cat 91, that telescope we just sold earlier this month in favor of the Cat 108. Both amazing scopes by William Optics, paired with an ASI 2600 camera, which we don't have, but like 90% of you out there have it. I think that's the most popular camera today, isn't it?
I think so, yeah.
You just see that all the time, and it's an amazing, amazing camera. So let's suppose with this telescope camera combination, we take a 1 hour image. So the time is 3600 seconds. The pixel size of that camera is 3.76 microns. The focal ratio of that telescope, Cat 91, is 4.9. K is just a constant we're copying over. This is the California Nebula, this big image right here. And I'm using so this is a rectangle that I drew on this image that I got from Wikimedia Commons. And roughly the length is going to be 3.4 degrees, the width is going to be 1.5 degrees. Plug all those numbers in here and you get a signal-to-noise ratio of 3.8. So that's a pretty small signal-to-noise ratio. As opposed to the Iris Nebula, the Iris Nebula is very small and quite bright. Yeah. So this is for the California Nebula. The surface, the old-fashioned guys would say it has low surface brightness, right? Tough to see visually. But the Iris Nebula is a whole different ballgame. Its length and width are about 0.3 degrees compared to 3.4 and 1.5. It's really small. Its visual magnitude is actually it's actually a slight bit dimmer than the California Nebula, because the higher the magnitude, the dimmer the object. Right. But it's even so, its signal-to-noise ratio is 20, which is quite respectable. Yeah. Through this same telescope camera combination, you're going to get a great signal-to-noise ratio on it, get a lot of detail. Why is a large signal-to-noise ratio important? And the answer is, I think when you were processing the dark shark the other day and I was looking over your shoulder and we had a little bit of noise and you did a little bit of noise extermination and just went poof, disappeared. Just went poof. Yeah, it was so amazing. But that noise that you see, which is kind of the pixelization, one pixel's bright, one's faint, one's bright, and it's kind of a random pattern that's superimposed. And you can tell it's noise because it just doesn't look like what the galaxy should look like or what the nebula should look like. But the higher the signal-to-noise ratio, the less noise you're going to see in those faint portions of the image. Now, here, the brightest parts of the nebula are going to have a fairly high signal-to-noise ratio because you're capturing a lot of photons. And it's really, haven't you seen this in processing, Ren, where you're looking at the faint wispies of something? That's where you see
the harsh part.
That's where you see the noise, and it's dog ugly. And
yeah, it's dog ugly.
Yeah.
Magnitude and signal, principle 150. The greater the magnitude of a celestial object, the fainter the object, and the smaller the signal-to-noise ratio.
Okay, so this one, we already talked about the fainter objects have bigger magnitude numbers. We haven't talked about its relationship to the signal-to-noise ratio. And this one makes absolutely 100% sense. If the magnitude is larger, the object is fainter, and the signal-to-noise ratio is going to be smaller. Yeah. You have to think about it as being, okay, I want a big signal-to-noise ratio because I want a lot of signal compared to the noise. Yeah, exactly. Thanks so much for watching.
And we'll see you next time.